We will start the second talk provided by Professor Huajian Gao from Tsinghua University. First, I will give a brief introduction to Professor Gao. Professor Gao is a well-renowned scientist in mechanics, materials, and engineering science. He is a member of National Academy of Science of USA, National Academy of Engineering of USA, American Academy of Arts and Sciences, foreign member of Chinese Academy of Sciences, a fellow of Royal Society, German National Academy of Sciences, and a foreign member of Academia Europaea. Professor Gao is widely known for his contributions to the field of solid mechanics, particularly on macro and nanomechanics, hierarchically structured materials, and cell nanomaterial interactions. Uh, Today he will talk about smart structures and materials for low altitude economy, interfacial engineering for perching and grasping. Let's welcome Professor Gao again.
Thank you. Thank you for your kind introduction. Actually, I was a little bit embarrassed when I was invited to give a talk here, but I totally forgot it. I didn't even upload my abstract. I was reminded a couple of days ago. So sorry for this chaos. Okay. So I moved to Tsinghua University about a year and a half ago, before I was in Singapore. So the talk I'm giving here today was done by a former student who's still in Singapore in NTU, Huajian here, my friend. And Professor Shah was a co-advisor. So we co-advised student. He graduated, he's now a postdoc. Okay, so I'm now in Tsinghua University. We have this new research institute called Mechano-X Institute. Right. So I'm not from mathematics, I'm from mechanics. Okay, as you know, mechanics, classical mechanics is a science concerning forces, motion, and their relationships. And basic mechanical principles include laws of motion and universal gravitation. Newton was in the very old days, Newton was very optimistic about mechanics. So that's what he says in Principia Mathematica. He said, for all the phenomena of nature to be explained as far as possible by mechanical reasoning. Okay, of course, today we know that view is limited, right? But in engineering, that's turned out to be mostly true. Okay? In engineering, everyday engineering. So today, modern mechanics is no longer, let's say, a part of basic science, but we're at the bridge between basic science and engineering technologies. Okay, so mechanics is like this hub between basic science and engineering. We are mostly in engineering school currently. Okay, we're not in the school of science. And so basic science provides a knowledge base for engineering, right? Engineering provide needs. So, okay, I'll give you a very simple example. What's the difference between basic science, mechanics, and engineering? So, like Newton's law is now considered part of physics, right? Newton's law. But from this to engineering technology is still quite a far distance. Okay? You can't just cannot just design aircraft engine based on Newton's law. So you need something in between. So that's what we study. We study metal strength and fatigue, okay? Based on, this is a fundamental problem for materials. And we, of course, we're based on physics, but we provide a bridge to apply these basic laws to design aircraft engines. Mechanics play a quite important role in several industrial revolutions. First industrial revolution was basically had to do with Newtonian mechanics. Okay. Second industrial revolution, with mass production, these things, solid fluid mechanics has arisen during that time. And third industrial revolution with physical mechanics. Now we're in a so-called fourth industrial revolution. We have cyber physical space. Right now, mechanics community, we're talking about what is the corresponding mechanics corresponding to this era. Some people call cyber physical mechanics. So in a sense, I would say modern mechanics really is application-driven basic science. Okay. All right. So When I joined Tsinghua University, we established this Mechano X Institute, right? So it was funded, officially funded April 26, 2024, right? So it's co-funded by 8 engineering schools in Tsinghua, okay, plus biomedical engineering, and also Tsinghua medicine. Right? So the idea was to promote interdisciplinary collaboration between mechanics and these existing engineering schools, especially related to mechanical engineering. Right? You can see here we don't have electronic part of the engineering activity. Okay, so the name MechanoX, let me explain a little bit. Mechanics, we can understand X mechanics and mechano-X. And Professor Wei Yang, for example, who's currently at Zhejiang University, who's the actual president of the NSFC China. So he established the so-called X Mechanics Center, right? So the vision for the X Mechanics Center was mechanics now powering all subjects from physical science, life science, and social science, right? So we say we name this new phase for development mechanics X mechanics. So X mechanics, as opposed to classical mechanics, solid and fluid mechanics, not just everything. You can learn some physical basic principles and physical law from all the technologies. You can derive fundamental problem for all technologies. Okay, so now the relationship is X mechanics means mechanics of X, right? We learn from this one, we have some basic laws, basic principles. Now the other way, from mechanics to X, there's a mechano-X, means mechanics for. As you know, President Lincoln has this government of the people, by the people, for the people, right? So you know the relationship. X mechanics, mechanics of X, mechano-X, mechanics for X, right? Essentially, we are going to apply the basic principle in mechanics to help develop new technologies. That's my talk today, focusing. Actually, this idea is not new. It's not new for me. Actually, has been developing for more than 3 decades. In the old days, we have the mechanics material, for example, but that's mostly focused on passive understanding. Okay? We have a lot of concepts like stress-strain relationship, hardness, fatigue, elasticity, plasticity, fracture, etc. But since the 1990s, with new technology development, we have the way to manipulate cells, right? So there's a branch called mechanobiology to understand how biological activity are influenced by mechanical signals, right? How to use mechanical signal to manipulate biological systems. That has become a big field right now. There's several journals, a lot of laboratories. For example, National University of Singapore has a big mechanobiology center. Right? And mechanochemistry is not a very old idea, actually, over 100 years old. People know the mechanical properties of materials or mechanical signal can influence chemical reactions. But 10 years ago, it became officially established a field in a sense, it has created their own journals, Journal of Mechanochemistry and so on. Right? And I want to talk about this idea of mechanomaterials to design material with emergent function based on mechanics. So this idea comes from during the COVID, so during the lockdown time. So Professor Xiaodong Chen and I from NTU and I have a lot of discussions. So we're just talking about how would mechanics integrate more closely with materials. In the old days, material science and mechanics are separate, independent disciplines. Right? How to develop materials is basically through empirical trial and error approaches. People just cook in the kitchen. Right? You try to make different recipes, making material using trial and error. So the old paradigm, mechanics and material paradigm is material scientists make the material, then mechanics people go with modeling, characterization, and then help design and find applications. The mechanomaterial paradigms is like a turn us upside down. We're going to integrate mechanics at a very early stage, before the material is fabricated. Okay, we're going to integrate mechanics and material at a very early stage. Then it depends on application scenario. We're going to design the material as needed, then develop fabrication techniques. Okay, so in this envisioned new paradigm, especially in the age of artificial intelligence, mechanics is not considered merely a tool for passive description, right? But an active driver that deeply integrates with other scientific disciplines, enabling controlled regulation, programming, and optimization of target systems in material science, chemistry, biology, medicine. So you can think of the following. We have a mechanics principle, basic principle here. We understand like a relation between force, geometry, and property. Then in principle, right, so far we can fabricate a material using this to understand, then do forward design. But what if with the assistance for machine learning or AI, we could do inverse problem? We could start with target functionality, whatever function you want, you desire. Then ask a question, how do we make the material? How do we fabricate the material to achieve this target functionalities? This usually involve a higher dimensional space, some optimization design. So this inverse design will be we think will become increasingly important for the future. Right. Before I talk about today's topic, let me also mention a couple of other research we've been doing. One is we've been looking for design of fatigue-resistant metals. As I mentioned, metal strength and fatigue is very important in engineering, right? You design anything, that fatigue is the most important property. In fact, over 90% of the materials or structures fail by fatigue, right? That's why the airplanes or the bridges, they eventually fall down. Fatigue is like an aging issue for a human being, right? Aging is one of the most difficult problems for biology. So fatigue is equally important problem for engineering. Right. So far, there have been very little progress in this field. But we understand how fatigue happens. Fatigue is because these microscopic defects, atomic defects, atomic defect in the material, they start accumulating and pile up against boundaries, green boundaries, or they pile up against each other. They have a like cross slip. You have this defect. They pile up against a cross section. These intersection points are to become a sites of a high stress concentration. They develop cracks. That's how material develop these defects and then cracks, the micro crack, then eventually fail. Right. However, we found it is possible, indeed possible, to design a microstructure to avoid this. Okay. For example, I have a little simulation here. Okay, this shows if we can design, instead of random boundary, we design parallel boundaries. Okay, parallel boundaries. Like, for example, so-called twin boundary in material science, like this structure shows. Then we could organize dislocation in a sense, it become all highly organized. The dislocation only travel like trains or cars in the highway or trains on the railway. So they become highly organized. They do not entangle each other. So you totally avoid these intersection points, right? First of all, the dislocation all move parallel to the boundaries. They do not intersect with the boundary. Second of all, there are only one single slip systems. You do not have a multi-slip system. You avoid both scenarios. So in this case, our collaborator from Institute of Metal Research in Shenyang, Professor Lei Lu, helped us test these ideas. So she found indeed, so here's a coarse grain traditional metals and the ultra fine grain metals, and that's the nano twin metals. And she fabricated in the laboratory, proved this nano twin structure have very unique property. Okay, even with more than 20,000 cycles, there's no damage in the material. The material becomes totally reversible. Okay, this demonstrating that fatigue problem can indeed theoretically be addressed, but still to be able to apply industrially still need some time, more time. That also gave us hope maybe one day we could solve the aging problem, right? That's the even more difficult problem. Another problem I've involved is the mechanics-aided discovery of antibiotic. Okay, here's a challenge is all the traditional antibiotic, they target on some biological pathway. synthesis pathway, right? One of the drawback for conventional antibiotic is when some bacteria went into hibernation, right? You just stop stop the metabolism in the bacteria. Those bacteria are called persisters. You can think of persisters are sleeping bacteria. If you give them antibiotic, if the bacteria went to sleep, then it's not become immune to antibiotic. It develop anti-resistance. It develop a drug resistance. It will survive. So they were very hard to kill by conventional bacteria. Okay, but now we're facing a potential health crisis because some of the bacteria become superbug, right? No existing antibiotic can treat some of the current superbug. Fortunately, they're still in the hospital environment. They have not escaped to our world, right? If one day those bacteria broke through and came to like viruses, right? Came to human society, they can induce a pandemic. Right? So the idea that our collaborator from Brown Medical School, Professor Manolakis, is can we target, instead of target synthesis pathway, can we target biological bacterial membrane? Because even sleeping bacteria, they still have a membrane, dependent membrane. If you can destroy their membrane, then bacteria, even persister will be killed. Okay, so the idea is that we come in and help him to select which molecules will be able to invade into bacterial membrane and cause this kind of aggregation, local curvature, and cause fracture of the membrane. Okay, but still the challenge is you cannot destroy human membrane. You only target bacterial membrane. So it turns out we were able to identify a couple of candidates, good candidates. For example, this is free energy. When you have this molecule invading the bacterial membrane, you can see this, for example, this blue and the red, these two, they have an energy sink inside the membrane. This is a good candidate for antibiotic. For others, the energy is increased when they invade the bacterial membrane. That means this particle will not be able to penetrate into bacterial membrane, okay? So here's some simulations. And here's some experiments. So underneath are experiments. These are simulations. You can see that, for example, this case corresponds blue curve. This blue, right? CD437. They were able to invade into the membrane and cause this kind of rupture. You see the aggregation. Aggregation in the membrane, they cause perforation in the membrane, right? So based on this kind of design that our collaborators have explored and have then discovered, this is indeed a very good candidate for antibiotic, right? You can see that it can kill persisters. After some dosage, it rapidly kills persisters, has a very low human toxicity, has low resistance, right? This is very important. Conventional antibiotic develop resistance in 2 weeks, right? That means if you get sick, again, you need higher drug dosage. But this drug remains no resistance up to 100 days. Right? This is the key revolution of this finding. And so we published this paper, and now, of course, it will take some years for FDA to approve. Another topic I was pretty excited was we designed a biomaterial for heart tissue restoration after a myocardial infarction. This is the heart attack, essentially, a name for heart attack. Okay, currently, myocardial infarction is still the biggest killer of human being. Right? The global death rate is the highest among all diseases. The heart attack still, the cardiovascular disease still the biggest killer globally. Right? So what happens is the heart attack happens when the artery, the coronary artery supply nutrition to the heart become blocked. They become blocked. Once we get old, the blood arteries become blocked. Then some of the heart tissue will die. When the heart cell died, the cell wall is weakened. Right? It cannot sustain enough mechanical load. So as the heart keep pumping, the heart wall chamber become thinner and thinner, and the heart become larger and larger. And then after a couple of months, the patient suffer death. Okay, so we were able to using simulations to identify a specific material called gel point material, gel point polymer-based gel point material that's in between a solid and fluid. This is the ratio between storage module and loss modulus. You know, for the solid, you have basically storage module but no loss module for purely elastic material, right? For fluid, you have loss module but no storage modulus. But when there's two modules equal to 1, that's gel point. That's halfway in between a solid and fluid. It's not a solid, not a fluid, but halfway in between. That's a viscoelastic material. So we identified this is the best material to treat myocardial infarction. So our colleagues, we have collaborators, Professor Lei Yang from Suzhou University, and cardiologist, Professor Min Sun from Fudan University, have a test. So Professor Lei made this material, gel-based material, with the G double prime and G prime exactly the same, right? Across a wide range of frequency. The heartbeat is 1 hertz. This is the heartbeat. But this ratio maintained equal to 1 for he was able to make this material over a wide range of frequencies. Then we test for the rat, in the case of rat, we showed the so-called GPAP, so gel point adhesive patch, right? This blue material outperform all the others. So this is untreated, okay, untreated. This is measure the thickness, the ventricle thickness, the heart chamber thickness after 4 weeks. So if the heart is untreated after heart attack, the chamber become very thin, okay? And this is a comparison materials. This special design materials outperform everything else, become best. So this is the comparison chart for all the existing therapy, all existing materials. So our mechanics-based design outperform all the other materials, okay? So this means if you can use mechanics to help design material properties that can best help our tissue restoration and also health recovery. Okay, so let me mention an example, then I'll go to the theme today. So this is my last example. So a year ago, we helped Professor Lei Wei from NTU to fabricate semiconductor fibers. The semiconductor fibers become very important for optoelectronics. As you know, currently the future wars are going to be fought by drones, right? You see the Ukraine-Russian conflict. The drones become very important. But drones, you can actually, if it's regularly designed by regular chips, it can be easily disturbed by electromagnetic waves. Okay, but so optoelectronics is a secure way for the drone to communicate. Right? But you need semiconductor fibers. But currently, there's no good way to make long fibers. So it's very, very challenging to make fiber. You can make chips. Currently, you can make silicon wafers by crystal growth. But imagine you use crystal growth to grow long fiber. It's going to take many years. Okay. So how do you make good quality semiconductor fibers? So we thought of a way using optical fiber, fiber drawing under high temperature. Okay. You embed a semiconductor like silicon and germanium inside a glass cladding. Outside is glass. Okay. You melt both systems. So you have a fluid, you have a semiconductor fluid in a fluid form embedded by the viscoelastic material shell. You draw, okay, you draw into wires. And so here you have a molten stage, then you cool it down into solid. Okay. But you have two challenges in this process. One is in the fluid stage, you can have droplets. In the fluid stage, you have instability. You have this fluid-like instability, so-called Taylor-Rayleigh type of instability. It's just like water drop. You open a water fountain, right? This water can break up into droplets. Same kind of instability. When you do the thermal drawing, this fluid state can break up into droplets, okay? Like the experiment shows. Also, another challenge is when you cool down into solid form, you can have cracks. You see here the two examples, you have a lot of cracks, very dense level cracks, okay? Either when either fluid instability or fracture happens, you cannot have long wires. Maybe you have a very small pieces, right? You cannot have. So to overcome this issue, you have to design. You have to really design the whole fabrication process. So we did a study, and we used mechanics, fluid mechanics, solid mechanics to help design the fabrication. We were able to help the people to fabricate very long semiconductor wires. So this is the results. Actually, hundreds of meters, thousands of meters of semiconductor wires for that process. Okay, so let me come to today's theme. I want to talk about low altitude economy because this is a big thing in China now. Many cities are promoting 低空经济, low altitude economy. Basically means you have flying vehicles below 1,000 meters. That's low altitude economy. Okay, many cities are talking about that, especially Shenzhen and Wuhan, right? And so this is supposed to be $1 trillion market very soon, and you can extend to 3,000 meters flying. But basically, this is a very low level. No airplane would fly that space. Currently, is available for home delivery and things. So here, of course, there's many challenges. Highly interdisciplinary area. You need to design the flying vehicles, drones, basically, right? Against design drones. And so a lot of control issues, power issues, energy issues. But two problems related to mechanics. One is structure, one is material. You need a lightweight material, you need design structures, right? So there's a lot of new challenge opportunities in this field. Specifically, the lightweight material is very important, right? It cannot be very heavy. It costs too much energy. Low density, high strength materials, and also you need to be tunable, active structures. Right? You need to design smart structures that can achieve different functions. Okay. Oh, sorry. Also, interfacial structure material is very important. This is my main topic today. One is the drones need to be pick up goods, pick up boxes, right? Pick up things like home delivery, deliver things. That's the main utility of the drones. You need a way to grasp things and perching, right? Like temporarily resting on some platforms. So grasping and perching have emerged as two issues in the design of drones. So far, there's a number of strategies to design these interfaces. One is a mechanical way, suction and adhesive ways, and using this, right? So let me show you one. Right, this is one video, just kind of show you get a feel how the drones. Right. These are mechanical grippers. And using the same grip to perch. Okay, you can see that one of the drawback is this gripper is heavy. Right? This mechanical device is pretty heavy by itself. Also, its size is limited because if you grab a flat, big object, it's trouble, right? You need some kind of handle to be able to function. Okay, so let me just move ahead in the time. So existing designs for mechanical grippers, many people study this, right? Various kind of designs, like biomimetic design, and talons and bird-inspired designs for mechanical ways, design even dynamically pick up some objects. And the suction cups, it's like one example is a little fish here, right? Using suction cups attached to a big whale and just take a ride, right, in the ocean. Right? That's kind of the idea. So, oh, sorry. Okay. So here you can see this vehicle, right? Just fly out of water and attached to this rock by suction cup. Right? You can perch on this rock. So suction cups, and the drawback of this is you need a flat surface, relatively flat surface to do that. And also magnetic devices. Right? So you have surfaces that magnetic, and then you can use the magnetic forces to design the interface. And magnetic grippers, they can have high load capabilities, right? And but they're also heavy. These things can be heavy as well. Okay, here's adhesive. If you look at nature, the insects or birds, especially insects, so mostly the insect use adhesion for interfacial interactions. Right? Like bees and flies, they actually use adhesion, right? You may think they use some kind of mechanical gripper, but they actually use adhesion. You can see currently adhesion devices, the adhesion is quite weak, only 84 milligram, right? So load capability, that's the main limitation for the adhesion devices. Okay, let me just proceed. So, yeah, adhesion, you can use muscle inspired, various adhesives, insect inspired or inspired by muscle. And here's a you can adhere to the top of the car. So, okay, so let me summarize all these various designs here. Vertical axis is load capability, how much weight you can carry, right? Which is very important for low altitude economy. This needs to be large, load capability. For the horizontal axis is object size, a gripper size. So by seeing this, you can see the mechanical grippers occupy this domain, right? And the other three, magnetic, suction, and adhesion, occupy here. Okay, so mechanical gripper can provide large load capability, which is true. Right? But limitation is mechanical gripper cannot be designed very large, handle large objects. But magnetic suction and adhesion can handle larger objects, which is very important. So both are important. Larger high load capability and larger objects are both important for low altitude economy. But currently, there's a limit. So let me put a table, compare mechanical, suction, magnetic, and adhesion. Okay. Control complexity, mechanical is high complexity, but the others are low, right? Of course, the low is better. Simpler, the better, right? The more you means you have the more design and more complications. And target adaptability, right? So this need to be, the object you handle need to be smaller than the device, which is a drawback for mechanical. And this suction cup needs a smooth surface, and magnetic needs to be ferromagnetic material, and this is universal, right? This adhesion stands out, okay? It doesn't need to be ferromagnet, doesn't need to be smooth, it doesn't smaller than device, and device mass, which means the gripper, how heavy it is. Mechanical is heavy, this is heavy, this is heavy, this is low. The lower the better, right? Energy consumption, this is high, medium, and this is low, right? This is good. Adhesion is all good. We can see adhesion is big problem, is low load capability, adhesion, right? If you think about, Guozhan will know from Singapore, gecko is the heaviest animal, right, for adhesion. It only weighs like 200, 300, up to 200 gram, which is quite low, right? For low altitude economy, that's not enough. 200 gram of grocery, right? You need to upgrade it. You need to improve. So we extract a mechanics problem. We think this is good, right? We're gonna adhesion stands off with simplicity of control, target adaptivity, and lightweight design, energy efficiency, but limited load capability. So we extract a problem that can we greatly improve this, okay, using mechanics. Now let's find a way how to improve the load capability. Okay, so now let me put a challenge here, for mechanics, extract the mechanics problem. First challenge is so-called adhesion paradox, okay? And this adhesion paradox is coined by Kevin Kendall in his book, Sticky Universe. Okay, Kevin Kendall basically says, in his introduction to molecular adhesion fracture, he basically says, according to Newton, Isaac Newton, everything stick to each other. All the molecules in this world, right? Atoms, you have a universal attraction. All the molecules, they attract each other, right? But how come we have deserts and the particles just loose, they do not interact? And we, in daily life, we don't feel adhesion. If you put a finger, touch on chair or table, you don't feel adhesion, right? So why is that? This is called adhesion paradox. Means our experience, our daily experience, are not consistent with Isaac Newton's or scientific understanding. All molecules adhere to each other. Okay. So according to Kevin Kendall, he says solid surfaces are expected to adhere to each other. The question is to explain why they do not, rather than why they do. Okay. We don't have good adhesion in daily life. Now, since about for the last half a century, this problem was now well understood. Because surface roughness, we think the material surface are flat, but they're not. In microscopic scale, they have roughnesses. Okay, they have roughness. So when the two materials come into contact, you think they are in all the molecules in good contact, but in fact they're not. They have so many spaces, right? Only a few molecules see each other. So surface roughness is a classic impediment to adhesion by short-range intermolecular interactions. That leads to much smaller true contact area. This is one thing. Second thing is more important, right? You see, I have small contact, but why can I use a force to push them together? I can push two objects, force them into close contact, right? But that still does not work because in that process, you insert lots of elastic strain energy in the contact interface. When you let go, that energy will come back, all right, cause the interface to be spontaneously repelled, right? So these are issues for the adhesion paradox. Another issue we need to overcome is the switchability conflict. This comes from, for example, if you look at gecko, one example, right? Gecko can adhere to a surface, can walk along the ceilings. So it needs to have a big switchability. This means gecko, when it's adhered, it wants to have a high strength, but it wants to walk or run. It has to easily release it, right? You need to have the maximum adhesion and minimum adhesion. You need to be big ratio, controllable, right? So maximum adhesion and minimum adhesion, that ratio is called switchability. Okay, switchability, right? But we have a so-called switchability conflict, which means the higher the adhesion strength, the more difficult it is to switch. Okay, so adhesion strength and switchability come into conflict. If you wanted to take on bigger, heavy goods, heavy grocery, then your switchability sacrifices. You cannot just release it. It's very hard to release it, right? And you can see the geckos here, right? Gecko here. And there's many man-made or laboratory material that can go into here or here, but we cannot go here. We need a big switchability and heavy load, right? So how do you do that? Okay, so the inspiration we adopt is called snail. Snail exhibits so-called phase transition adhesion. This is new. In mechanics, we have adhesion mechanics, but we have not actually considered phase transition in that process before. When snail establish adhesion on a wall, it does a phase transition. So what snail does, when the snail moves, it secretes an enzyme. So it has a mucus, it's surrounded by mucus. This allows snail to move along the surface. But when it wants to attach the surface, then it dried out. Okay, it has dried mucus. So mucus becomes a solid. It's when it's moved, it becomes fluid. But when it's once adhere, right, went to hibernation, it dried out. So this is in solid form, it's a strong adhesion. In the fluid form, it's weak adhesion. This is called phase transition adhesion. Right? So phase transition adhesion leads to pretty strong so this has been measured over 1 megapascal stress, and it's switchable in the sense you can do the phase transition, right? You can, if it's a solid, it's strong, if it's a fluid, it's weak. So it's strong and switchable. Okay, but we do not want to use fluid. We don't want to use fluid, solid fluid interaction, right? One is we want to be a highly tunable solution, right? So we consider so-called shape memory polymers, SMPs. The shape memory polymers basically it's a polymeric material. Okay, so I have some video here. So this material you can deform. There's a TG. It's like a melting temperature, but it's a phase transition temperature TG. Above the TG, the material is very deformable. You can deform it to some shape, right? And then when you cool down below TG, that shape will be frozen. A deformed shape will be frozen. And then, but that original shape is still stored in the memory. So when you heat it up, the material will spontaneously return to the original shape. Okay, so let me explain this one you're seeing here. Right, you deform above TG, all right? Then you cool it down so the material, you can see this length remains. Then we want to restore original shape, you just heat it up. Okay, it remains. So this material exhibits the deformation, shape locking, shape memory, 3 phenomena. Deformation is highly deformable above TG. When you cool it down to below TG, the shape can be locked, temporarily locked. So elastic energy can be frozen temporarily. But but the energy is not lost. But when you want to release energy, you just heat it up above TG, and the energy you just recover the original shape. Okay, so this material has been used for adhesives, right? People have been trying adhesive, making various usage in the last 2 decades, right? 2 decades. But strangely enough, its mechanics behind it, the mechanism behind it, has not been thoroughly understood. So we do not know how to control it in this. So it turns out this shape memory polymer overcome surface roughness, perfectly overcome surface roughness in the following. Okay, so for example, we take this so-called E44 shape memory polymer. Okay, very simple chemical formula. It's essentially a polymer network. Above TG, you can heat it, right? To do some deformation, you can stretch it. Then you cool it down, so that deformed shape will remain. Okay, then you raise it above, heat it up above TG, it will recover its original shape. This is the deformation, right? Shape locking and memory, shape release. Okay, so this one you can use in the following. Imagine you do a phase transition to adhesion. In a glassy state, okay, this is very high modulus, but cool down, right? The bluish means the temperature is relatively low, it's below TG. In this case, this is pretty tough. This is rough surface. There's no adhesion. Very small adhesion. Okay, in this state, very small adhesion. If you just you can do the interaction. You put it up. Very weak forces. But now imagine you heat it up. Okay, you heat it up above Tg. Then you press it. You form a conformal contact. All right. If you let it go right now, the elastic energy stored in the interface will rebound. Right, will become released. So you don't have good adhesion. But imagine you just cool it down at this state. You don't before you let go of this force, you cool it down. Now the deformation will be frozen. Okay, all the elastic energy interface will be temporarily locked, without release. If you now pull it here, you have very, very strong adhesion. You have a super strong adhesion, right? Because the energy is being stored, has been frozen in the interface. Now, if you want to release, then you just heat it up. Simply, you heat it up. The energy, you just kind of wake up the elastic energy stored near the interface. The material will spontaneously rebound. Okay, so this is the key. You do a temperature cycle. You press at a high temperature. You cool it down. You have very super strong adhesion. Then you can release it by heating. Just simply heat. Okay, so here's a demonstration. So that's a conventional adhesion. Conventional adhesion. We make a rough surface very, very big for you to see, right? There we make a sawtooth like a substrate for you to see. This is a conventional adhesion. You see, you push it down, you let go. You see the interface is spontaneously released. Okay, spontaneous release. There's no adhesion, even though you push it hard. Traditional adhesion, right? Okay, you see here, spontaneously. Now let's turn on this phase transition adhesion. And you push it down, you establish contact, but you don't let go that moment. You cool it down, okay? You cool to glass phase. Remember, all the energy will be locked, temporarily frozen. Okay, in this case, you let go, see? You have well bonded, this interface, well bonded. Okay, how do you release it? You just simply heat it up. You heat to the rubber phase, the energies wake up, right? Become spontaneously detached. This is the idea of phase transition adhesion. Okay, now we measure adhesion strengths as function of surface roughness. You see, this is all traditional technologies, existing technologies. They all suffer from the adhesion paradox. The higher the surface roughness, the lower the adhesion strength. With the exception of our phase transition adhesion. In the case of phase transition adhesion, first of all, with surface roughness increases, actually it does not decrease, it increases. Because interface becomes longer. Okay? We have the rougher the better. You have more contact, more interaction. Second of all, the absolute magnitude of the strength has increased by 1 or 2 order magnitude. Right? See here, this is a logarithmic scale. Right? Increased by a lot, substantially increased. Okay. So the phase transition adhesion outperform traditional adhesion by more than an order magnitude. Okay. Now adapt for low altitude economy. You want to pick up goods like grocery. You need to be able to interact with all kinds of surfaces. You cannot just only interact with the magnetic surface, right? Or you can see that even traditional rubber adhesion, they're pretty sensitive to different surfaces like wood, stone, brick, right? Pottery, steel, polyimide, acrylic, right? Depending on what surfaces. The conventional rubber adhesion is quite sensitive, right? But the phase transition adhesion basically stay very strong, right? The true reason is basically use van der Waals force. You press it, you cool it down, right? This van der Waals force is pretty stable and highly adaptive to arbitrary surfaces. Okay, the switchability, as I say, because the shape memory effect, the energy is not lost; it's stored in the interface. You can release it, right? So you can design. So in phase transition adhesion, you no longer have the conflict switchability. You don't have that anymore, right? This is the traditional material, but if you use phase transition, these two become completely decoupled. You can have high strength, but this switchability can be designed completely decoupled. Okay, so you can design as these fibers. The fibers will allow you to further enhance the strength, but also design switchability. Okay, as opposed to gecko's fibers, the hair on the gecko's feet is a micrometer scale. So this one, because phase transition adhesion, you can upscale it to millimeter scale, very easily fabricated. Millimeter, you don't need a microfabrication lab. You just make it in the laboratory. It's millimeter size, right? So the strength stay very high, up to millimeter scale. You can design these little fibers to enhance the controllability, to tune the switchability. Okay, we can design these kind of arrays, and by changing the aspect ratios, we can introduce buckling, all kind of instabilities to further tune switchability. Okay, switchability. And now you can test. You can actually pick up very heavy goods, up to 60 kilogram, easily achieve tens of kilograms of weight, and it's fully reversible, right? This is the amazing part, this design. And so we designed a versatile adhesive robotic skin that you can have interactions, right? We can have like a three kind of state. One is glossy, it's a minimal, very weak adhesion. Almost you cannot feel it. And rubber adhesion is pretty weak, and phase transition adhesion is very strong. You can have develop some kind of robotic skin that interact with environment with three state. No adhesion, weak adhesion, strong adhesion, right? And you can also pick up, this can pick up very delicate, fragile objects, and as well as large objects. Okay, like a basketball, right? Because it's adhesive, so you don't need to be larger than this. You can pick up large objects. And okay, so anyway, so we call it a universal adhesive gripper. Imagine any object, any shape or form, because you can, in the rubbery state, it's very soft. This is a very soft rubbery state. So you can just, by pushing it, you can easily embed all the object into the gripper. Then just cool it down and freeze it. Then transport some another area, then just heat it up. All the object will be released, right? All the object. It doesn't matter it's macro, meso, or micro, right? So this kind of become a universal adhesive gripper. But still a very important issue we have to solve first. How long does adhesion last? The durability, right? You need to, with transport of grocery, you need to very reliably carry goods for some time, right? That thing adhesion cannot fail. The adhesions sometimes you have to be very reliable. So you know, from our experience, there's a three state of adhesion. One is you have is immediate detachment. Right? If you put a rock on some surface, that rock, even sticky surface, a little rock will very quickly detach. This is what you can see in the daily life, right? I don't have a video here. And or sometimes you can hang some bottle above ceiling. It looks steady, but after a certain critical time, it just suddenly falls. Okay, this is kind of and perpetual adherence. This is a long time adhesion. This is very difficult to achieve, right? But this is achievable because if you look at classical painting, like in museums, all the paintings, you can see that they're basically little particles, little small particles adhere to the canvas for thousands of years. Okay, so you can have this immediate detachment or sudden detachment after some time, or just forever, long-term adhesion. How to achieve three state? That problem has not been solved. Okay, how do you achieve permanent adhesion? How do you have immediate detachment and creep detachment? That turns out to be an issue. Even though for centuries people are interested, has not been fully resolved. Okay, so let me summarize here. So because of time, I won't go into this theoretical background. So we have three cases, right? First case is immediate detachment. right? You have a little particle here, but you have detachment going on right away, the interface. The particle fall, right? Very short time. The other one is after the particles stick for very calmly, peacefully, but for some time, then it falls down, right? Both of these are dangerous, but this is desirable. The third case, for permanent, right? This interface stay permanently on. That's very important. Okay, so we have done a systematic study of this. It turns out that adhesion is a competition between bulk creep, okay, deformation in the bulk of the material, and interface viscoelasticity. How the interface is a competition between bulk and interface. If the bulk creep dominates, in the case 3, we see when the bulk creep dominates, the contact area under tensile force actually increases. It doesn't decrease. Okay, so that means that when I pull two objects apart, you would think the contact will shrink, right? But if the bulk creep dominates, actually interface grows in the contact area. This is very counterintuitive. Okay, the reason is if the bulk creep dominates, the system wants to minimize energy, wants to minimize surface. Okay, by having the contact area growth, the surface energy is being reduced. Okay, so as opposed to the other two cases, if the interface dominates, if the interface visco dominates, then under pulling, basically you have delamination. The contact area is decreased to 0. In the case number 2 is initially the bulk creep dominates, but then the interfacial become dominant later stage. Okay, you have the 3 competition. If you can design a system such that bulk creep dominates, you can achieve permanent adhesion, right? That's no problem. Okay, so here I have just last video, and I'll conclude. This is the schematic video for a vision for a low altitude economy. When you want to grip something, you okay. You make an attachment and cool it down. You cool it down. You have a very strong adhesion. You transport to a place. Then just simply heat it up and you release the goods. Okay, so here's my summary. Low altitude economy has brought in new challenging opportunity for smart structure material. Among various design strategies, adhesives exhibit a number of advantages, but encounter 2 major challenges: adhesion paradox and switchability conflict. And we have found that phase transition adhesion based on shape memory polymers overcome both challenges at the same time. Okay, in a sense, the first challenge is because the phase transition, you have 2 states. Below TG, you have very strong adhesion. Above TG, you have weak adhesion. You can overcome surface roughness. The switchability, because shape memory effects, right? The energy is stored in the material. Just by simply heat it up, you can release those energy, help you to overcome switchability. So with that, so we have actually lots of publications, just in case. Yeah. So that's all. Thank you.
Hey, thank you for Professor Gao to give such excellent talk. Is there any question from all?
Prof. Gao, thank you so much for the nice talk, right? I learned a lot over here. Right? I have actually 2 questions. The first question is about the adhesive, the SMP. So I think that heating will be very quick because we can use Joule heating to do that, right? Cooling might be longer, right? That could be a challenge, right? I think. So I have 2 suggestions on this, right? So the first suggestion is that we can actually have a Peltier device, something that can cool. So we can heat and cool. That may actually overcome that issue. Another thing is like I saw like you want to, like the inverse design way. I was just thinking whether you can actually create SMPs with lower TG. So if it's nearer to our atmospheric temperature, right? Then that will be much easier to switch.
Yeah, thank you for that. Thank you for the suggestion. That's a very good suggestion. Yeah. The reason we choose ASMP as opposed to liquid case, right? Like a water frozen, always 0 temperature, right? But ASMP you can adjust TG. You can tune it by tuning the chemical composition of the material. You can vary the TG to the level you want, right? Either above the atmosphere or below atmosphere. If the cooling is a big problem, you design TG to be above the room temperature.
Right, just
so,
above it.
help the heat. Yeah, if the heating is a problem, you design lower, right? So that can help you. But also there are other ways, like the shape memory polymer. There's also can be controlled by electromagnetic fields, opto by sound, acoustic waves. There's other SMPs mechanism control the phase transition. The idea is, if you can use a phase transition, induce a phase transition in the material, you can overcome surface roughness. Right. That's the main message. Yeah.
Yes, yes. I think that's I agree. The second point is also about the inverse design method, right? So, Prof. Gao, you may, I don't know, from a soft robotics perspective, right? We like batteries that are soft also, because if they are, sometimes we want like to deploy untethered robots, and we may wish that the whole body is soft so that it can squeeze through holes. So now the batteries are always rigid, so we cannot make like totally soft robots. They have soft batteries that are soft in surface and deformable, but the power capacity is low, right? It's very low. So I can't solve the problem. I'm not an electrical engineer, right? But I don't know. I mean, if you are interested, it'll be great. You can solve this for us, right? Yeah. Okay.
Interesting. I'll talk to you.
Is there any other question?
Yes.
Hello, Professor Gao. A very nice talk. And my question is that does the switching of the temperature cost extra energy? And does it conflict to the feature that this method energy saving?
That's that's actually a very good question. Yes, the temperature, of course, changing temperature does cause energy. It does cause energy. Yeah. So, but there are ways. If you use micro heater and things, there's various ways you can make it does not add too much energy to the cost. Yeah. Of course, I gave this lecture to some venture capital some days ago. They're very interested in this kind of thing. Yeah. But how do you eventually optimize a system? This has not been optimized. What's the limit? How much energy cost it will eventually be? Right? There's various way of design things. Depends on design. And we're basically showing the feasibility. I think feasibility, the possibility, but you have to optimize it. Eventually, if you use commercial, you have to optimize it. How do you minimize the energy usage in controlling temperatures and things like this? But each strategy has different pros and cons, right? So from this point to really engineering, it still takes some additional effort. Yeah. Thank you.
Okay, thank you, Professor Gao again. If there is no
thank you.